Hello, welcome everyone. So we're very happy to have Carolyn Otto here today, and she will talk about Unsolved Mysteries, an exploration of theoretical and practical knot theory research. And how would you like people to ask questions?
So they can just unmute themselves and ask, or if you want to monitor the chat and just interrupt me, that's totally fine. This can be very informal.
Sure, sounds good. So go ahead.
All right, so first of all, thank you all for having me today. I'm always excited to share a little bit about knot theory, both in theoretical work and practical applications as well. I'm Dr. Carolyn Otto. I work at the University of Wisconsin at Eau Claire. This is also where I did my undergraduate, and I did my graduate degree in Houston, Texas at Rice University. So in the lower left, picture of me and my dog Ellie. I try to include my pets in every talk I give, so they'll sporadically come up as well. Um, so first, just a little bit about me. So mathematics is one of the things I use to define myself, but I'm so many other things, and all of these things kind of come and incorporate into my work as well. So just a little bit about me here up on the screen. Um, for your enjoyment. Okay, so what I plan to do today, I want to give you a little introduction into knot and link theory. Pre-recording, I believe, Marcus, you said you worked with Allison a little bit, so there might be a little familiarity about knot theory, but I'll do a basic intro. I'll show you some little history about it, and then we'll go into invariants, my work, my future work, and something I'm really passionate about, which is applications. So if you want to have any more kind of insight into things, please just pop in a question. I'm going to do a brief overview, kind of put in a little algebra in there as well. So, what is a knot and link? I kind of give a three-step procedure. So, there's the definition I give my parents, there's the definition I give my students, and then there's the definition I give my research students. So, an intuitive definition, tie in your shoe, fuse the ends of your shoelaces together, that's a knot. Working definition will be a knot is a simple closed curve in three space. So this just means that there are no kind of floating ends around, and it doesn't self-intersect. That's what simple means. And our technical definition, a knot is actually a function. It's an embedding of a circle into three space. So I have some just pictures on the slides of examples of knots just around my house and around my university as well. What I like to study are links, which are just a collection of co closed curves, simple closed curves in three dimensions. So here I have some pictures of a knot is a link of one component that's on the left. I got this 3D printed at my university, so we parameterized the knots and then they printed them. A link just has more than one circle twisted up around. Here it's indicated by two colors. If you can't distinguish the colors, there's one component that goes around, and then the inside stuff is the second component here. So the number of these knots that are kind of tangled together, we call them components of the link. So these are all around us. The basics of knot theory as a mathematical sense really started in the 1800s. But you can see them in the 16, 1700s a lot with sailors' knots and things like that and captain's logs. But we do have some cultural references here. Down here in the middle, this is a Kipu, South American kind of counting database system that they used with different knots in different positions to record keep. Celtic, oh, I heard something. Was there a question? Oh, okay. We have Celtic knots, right? So we get some Northern European um, imagery here. Chinese knots are a big thing in their culture. And just because I'm an Olympic kind of really like the Olympics. So here's a picture of the Olympic rings, which would be a five-component link as well. So links are three-dimensional objects. They live in three space, but to write stuff down, we live in two dimensions in the plane. So we do have projections and diagrams. So I created a couple images here of a 3D link and then the projection, how we would look at it in two space. So you get a lot of the strands and you stop at a crossing. So this part right here would be the overcrossing and then the undercrossing. And that's indicated here. So these aren't stoppings of the knots. These are just going under. So that's what those gaps represent. And we can start to classify knots. So this is our knot table. So all of these knots are different. So they're classified by two numbers. The big number is crossing number, and the small number is just an indexing set of how many of those knots there are. So for 8 crossing knots, we get that there are 21 of them. And then similarly, we do get links as well, and they're categorized by a crossing number as well, with a number of components in the upper, and then indexed by how many there are of 7 crossings with 2 components. So try to go back here. Okay, so this is kind of the big question of knot theory, is if we have two knots and links, how do we tell if they're the same or different? So if they're the same, right, we can untangle one to become the other. So my friend likes to describe this. We celebrate Christmas in my household, so but think of any holiday that has lights. So you take a set of holiday lights out of the box. Ideally, you know you can make them one string, but after you take them down from the tree or your windows, they kind of curl up into a ball. Theoretically, we know we can make them one nice string again by just kind of untangling stuff. This is what my mom thinks I do, by the way. The untangled jewelry is what I do as a knot theorist. So if I can do that, they're the same. But now how do I know if they're different? So on the knot table, we had like these were the first 3 knots. How do I know they're different? Because I can't just try to move it around and say, hey, I can't get the other one, so they must be different because there's infinitely many ways I can move things around. So I want to try to find a way to show that all 3 of these are distinctly different. So that's where invariants come in. So this is kind of a very big area of knot theory, are coming up with different quantities or properties that are the same if the link is the same, but could be different if the knots are not equal. So these could be answers to yes, no questions. This knot has this property, yes. This knot doesn't have the property, no. It could be a number, like the determinant of a matrix. It could be a polynomial. It could be symmetry groups, like dihedral groups of different orders, if you understand groups. It could be an integer sequence. It could be a matrix. It could be a number of different things. So as a knot theorist, we're trying to come up with more and more of these quantities to show that knots are not the same. So we do have a whole website dedicated to this. And again, I'll send Simon the presentation if you want to play around. All of these things are quantities and expressions and other things to show if knots are the same or different. So we can get a whole chart here. So the determinant of this 3-1 knot is 3. The determinant of this 5-4-1 knot is 5. So we know they have to be different because this quantity is different. And then we can look at all the different ways we can present these knots. So this website is a really fun one. We'll talk more about this mosaic knot here at the end as well. So we have a lot of invariants that we play around with. But what I am particularly interested in are these link invariants. So how do pieces of our link interact together? Essentially, how are they linked, right? This isn't a knot invariant, so you do have to have 2 components to do this. Okay, so here's how we're going to do it. It's all about counting. So on the bottom left, this is called a positive crossing. So if I put arrows on my components and I orient the two arrows up, positive crossing is when the overstrand has positive slope, and a negative crossing is when the overstrand has negative slope. So we would associate this with a +1. We would associate this with a -1. So the linking number, we're going to have all the positive crossings minus the negative crossings and divide by 2. Or take all the positive crossings minus the negative crossings when the ith component goes under the jth component. So I know I talk really fast. So now we're going to slow it down and kind of look at some pictures here. So this is what I call my butterfly link. It kind of has wings on the side. And I put arrows on my two components. So one component, L1, has the dotted line, and the L2 is the solid. So I'm going to look at the two crossings in my picture where the solid goes under the dotted. And in the middle diagram, I tried to shade those in. And then I just took their isolated picture. So the stuff inside the shade. And then I looked at where the arrows would be. And then I noticed if I rotate them 180 degrees, both of these are negative crossings. So my linking number would be -2. So it's a semi-easy invariant, just counting up plus and minus ones a lot, and testing, but links are going to be different if linking numbers are different. Now, I am a very big fan of historical math. So Gauss actually has an integral that can compute this. So I'm going to throw up an integral on our screen here in the next slide. So if you've had calculus, which I'm hoping many of you had, you know what an integral is. If not, just enjoy the beauty of this thing. If you've had a lot of math, this is actually going to be a multivariable double integral. So this is how Gauss computed this number. So for us, we just like counted plus or minuses. Gauss computed it using this formula, which is amazing, by the way. So in his journals, he kind of wrote up how to compute this number and started classifying knots using this double integral, which I won't talk in depth about. I really like this slide because no one really uses this to compute it. So there's not a lot of examples. Most just give the formula, but we actually found this on Reddit. A student of mine and I did, which I think is, super classy, Reddit, to find some math. But then we went in and found the mathematician who did it, and it looks great. So if you're familiar with multivariable calculus, we are going to parameterize our components. And then we're going to look at the cross product of those derivatives, and we're going to mod out by kind of our distance, essentially, and we're going to integrate this. And this will give an estimation for the linking number. It is a numerical approach, so linking number should be an integer. If you do it here, 3.99999, which limit would be 4. So here I'm looking at this bizarre little link here. So historically, this is what Gauss did to compute linking numbers. So this talk was going to be mostly about now what questions can I ask from this? So I worked with a student. Mostly this is all his work. And then I just kind of checked a couple of things. Wrote down the formula given by Gauss and his diary, and then wrote some Desmos programs to compute it. So this is a really good idea for a student project. He wrote a mini textbook to do this. So you guys have to write a 20-page paper. So my student David wrote probably about a 10-page paper on this till I told him to stop. And so what he did is he parameterized all these knots and then graphed them in Desmos. So this knot, this is called the granny knot. So the parameterization doesn't even really fit in one line here. Sorry, I got a little crazy here with the spinning. Um, but we can see the lovely 3D nature here. So we do have to parameterize with an X, Y, and Z. So that gets kind of complicated. There are easier parameterizations. So this is called the trefoil knot. This is, my students like to think of it as, this is the knot that's on Thor's hammer, right? It's a very common Celtic knot as well. But the parameterization, lots of sines, lots of cosines here on the side. Um, I like the 818 knot. It has some beautiful symmetry. Um, but as we look, it gets a little complicated in there. So my student parameterized all these so he could code them into Desmos. Um, so another good student project here is we did toroidal knots. So these are knots on a torus, so on a donut. So we can start getting crazy knots like this. And then let's get rid of the torus. Uh, they have some nice symmetry going on in here, but they fit on this like inner tube. So these parameterizations are pretty well known, but we can code them into the program. And then we can start computing linking integrals as well with different parameterization. So here's the Hoff link, and then it does have linking number 1, so it can compute it for us. So this is like Desmos 3D is a really great tool if you've never played around with it to graph in 3 dimensions, especially for knot theorists. This is really nice for us to play around with. So student wrote a mini textbook kind of working through these examples. Okay, sorry. Oh, yep. So I see some questions in the chat. Sorry, I'm really bad at monitoring the chat. So does the linking crossing number depend on how you look at the knot? So Marcus answered it correctly for crossing number. So the crossing number of a knot is over all projections of it, and you want to take the smallest number. Very true. There are these things called Reidemeister move. So like I could add a bunch of little twists in there, and that would up the crossing number. But we do look over the minimum. That's a common thing in knot theory is like look at the minimum over all the possible pictures. For the linking number, for a link, it should not matter the projection since it's an invariant that doesn't do the minimum here and it's between components. That number should always be the same. But that's a really good question because you'll see that a lot. Okay, good. All right, so here's my next question. Linking number, awesome. I can add plus or minus ones. This is a picture of the Borromean arrays. And the question now becomes, okay, so how do I consider linking when I have 3 pieces? And this is a very complicated question. So how do the 3 interact? And so this is the basis of a lot of my research. Um, and this is going to be called Milner's invariants. So if you've had some group theory, awesome. There'll be some kind of secrets in here as well. If you haven't had it, don't worry. We're going to pick some examples that are a little lighter. Okay, so again, we're going to look at this 3-component link called the Borromean rings. Notice if I erase any one of these components, I could then just kind of like separate them. But the 3 of them together create this like interlocking piece at the beginning that I can't separate. So what I want to do is I want to map out something called meridians and longitudes. So a meridian, I'm going to call those alpha. I am just going to find a curve around my component that has a linking number of 1. So I'm this kind of just a little circle around here. So notice an up arrow would be here, an up arrow would be here. So this would have linking one. And I put one of these on each of my components. Those are called meridians. Now, this choice is not necessarily well defined, but so we'll have a issue with that later that we'll try to take care of. But in general, we're going to just pick these generic ones. A longitude is we are going to create a parallel copy of our component where the linking number between the dotted L1 that just goes around kind of the big L1, that linking should be 0. So if there's like extra twists or something, we might have to counteract those twists. But those are called longitudes. Now, every longitude I can start mapping out in terms of these meridional discs. Now, this can be kind of hard. So I'm going to get to that next slide in a second. So I'm going to try to write out this L1 in terms of these alphas if possible. Okay. So, I don't know how much groups theory you have all had. Maybe none, maybe some. So I'm going to put up some reins and some stuff here, but I'll try to explain what's going on. So I'm going to take a function. It's going to be a homomorphism, but I'm going to take this function. It's going to go from ZF to Z x1, x2, and x3. Okay, so this ZF, so this is going to be called the free group generated by those alphas with integer coefficients. So what I want you to think of, these are all the possible words with alpha 1, alpha 2, alpha 3, and their inverses. So things that could be in here would be like 2 alpha 1 alpha 3 inverse, or alpha 1 alpha 2 alpha 3 inverse, alpha 1 inverse, just all the possible combinations of the words we can form with alpha 1, 2, and 3. Okay. Our codomain, this is going to be the ring in a power series. So we love power series, right? Power series are great. In 3 non-commuting variables. So I'm going to have x1, x2, and x3. So this map is going to take alpha I to 1 plus xi, and then alpha I inverse to our alternating power series 1 minus, xi plus xi squared minus xi cubed, so on and so forth. This is called the Magnus expansion. So it's a really nice function that kind of goes between these meridians and this polynomial. Here's where it gets a little bonkers. So if you are an algebra person, this is where it gets fun. If you're kind of a visual person, this is where it gets a little maybe less fun. I am going to pick L3 here. And I'm going to try to write it in terms of the meridians. So L3 is just exactly following big L3. So I'm going to go to this picture. So I'm going underneath here. And notice when I'm following underneath here, if I would just move this little blue circle down, I'd be traveling in the same direction as that. So that's where this alpha 1 comes in. I'm going over here. I'm going to see how I interact with alpha 2. I'll go alpha 2 inverse. Then I'll go alpha 1 inverse. It's like I would just like take this little blue ring and trace it down there. And then I interact with alpha 2 again when I get here. So L3 I can write as alpha 1, alpha 2 inverse, alpha 1 inverse, alpha 2. Now, this example was made so we could just trace. This is really hard. This is a really hard step. And there's a lot of stuff. If there's any kind of twisting at all in my components, this can become very difficult to do. And I actually think that's the hardest part, is writing the longitudes out in terms of the meridians. It is proven by Milner that this is always possible. You can always do this. There's like some relations that we have, always possible. Sorry if you can hear that barking, that's my dog. So then I'm going to take the Magnus expansion of that word. It's a homomorphism, so I can split it over multiplication here. And then I'm going to use those rules I gave you before and just replace them by 1 plus xi or that power series, alternating power series. And then I'm just going to do some algebra and simplify. So I get down here. So these can't cancel because they're non-commuting, which is a little strange. Normally we like things computing, but we can't here. And then we get a bunch of higher order things. So this whole long explanation goes into saying the following thing. I'm going to look at those coefficients in front of x1, x2, and that's going to be my linking invariant. So this is a little strange. So I looked at the longitude L3, so 3 is going to be the last number in my sequence. Whoops. And if I look at the order 1, 2, this is going to be my linking number 1, 2, 3. So that's going to be a -1. Here I go 2, 1. So this would be my linking number 2, 1, 3, which is 1. And those are my triple linking numbers. Now, these are only well defined for the first non-vanishing ones. So if I had an x2 squared x1, that's the number in front of that's not going to be well defined. So I do have to look at the not vanishing ones, the first non-vanishing ones, and that's because we pick where the meridians are. So this was super fast. If you're interested in, there's so many questions we can ask. So I know students who are working on triple linking numbers like this from a purely geometric standpoint. They can use multivariable calculus and Green's theorem and stuff. We can trace out words and look at surfaces. If you rather, I know you had a talk about persistent homology earlier. There are homological ways we can look at triple linking number, which is my specialty. We can also ask what happens to triple linking numbers when we do different operations on our links. And then we can talk about triple linking in virtual linking as well. And you can talk about not just triple linking number, you could talk about quadruple linking number, or like if you could talk about the linking number 1178432. Like we can make this as big as we want to here. And these are pretty strong invariants, especially the higher up we go. So some of my work with this
Um,
is I,
oh,
oh, I'm sorry.
there's a question. How is this homology theory defined?
Oh, yeah. So we're going to look at, okay, what a good question. So the first thing we look at is we're going to look at our fundamental group. And then we're just going to look at the abelianization of that. But if you're thinking like simplicial complexities and stuff like that, we are going to actually look at the space of the complement of the knot. And then look at that homology group. In terms of, okay, this is such a good question. I want to see if I can get my whiteboard here. Sorry, give me a moment to see if I can get this working. Okay. I can't quite get this working, but okay, so for the homology, what I'm going to primarily look at is I'm going to look at the complement of the knot in the manifold I am looking at. And then I am going to mod that out by something. I'm going to look at the lower central series of it. So this doesn't quite make sense without my pictures, and I apologize for that. So maybe I'll table that. I think Jack, you asked this question. It's such a good question that maybe I'll write up a little something in the interim about that. Um, Virtual knot theory differ from classical knot theory. Okay, good question. So cl virtual knots are going to be this was by Kaufman in 1999. It's a third type of crossing. So we have positive crossings, we have negative crossings, and then we have virtual crossings. And so we can view these a lot of different ways. So it's usually just a circle around an X. The way I view it in my research is with protein folding. It talks about the ambiguity of a crossing, like kind of like a Schrodinger's cats. Like it's both till we observe it, but we don't know. So maybe it's over and under. Or it's a way things cross in different handle bodies in different dimensions. But you can just think of it kind of as a third category of crossing. And it's kind of a really up and coming area for knot theory, seeing how we can take these classical things and change them with this new category. So there's not much that have been done with Milner's invariants in that regard. In terms of linking number, we kind of look at the classical crossings and not consider the virtual, or if you're changing it from, uh, if you're looking at not polynomials, we just categorize it in a different way and look at classical crossings first. But just a new type of crossing, which Marcus kind of added. Yeah, it's just a different kind of way of viewing things. The way I think about it, let's see if I can pull this up here. It's such good questions. We'll just go off topic for a second. Um, Hopefully you can oops, I'm showing my age. I'm really showing my age. Oh, that's because I'm in a different thing. Okay. Let's That's not gonna work. Okay. So think of proteins. Um, right, they're open chained, they have these endpoints, but to make them into mathematical theory, you need to connect them. But how do you connect it? Do you connect it over another strand? Do you connect it under another strand? So what I do is I plop on a virtual crossing just to emphasize that they have some kind of ambiguity there, and I don't really know what it is. It is kind of how I look at it. That's a good question. Are there other questions that you kind of want me to go into a little bit more here? Yeah, I agree. This virtual it's a whole new area of knot theory. And if we can get into like mosaics, we'll see it a little bit more. Yeah, it's so rich to these are, some of the things in knot theory, it's so easy to ask questions and it's like, yeah, I can understand what the question is, but then like the math behind it is like can get so complicated and it's really interesting. Okay, great. Um, so briefly, kind of seeing where your kind of minds are going. I'll go through this next part really kind of fast here so we can talk about things I think you might be more interested in. So I'm looking at Milner's invariants specifically in subsets of the group of links. So a group is just a way we can kind of categorize objects that act in a certain way. So it satisfies four conditions. So if you have two elements of your set, if you add whatever operation is your favorite, um, if you multiply them and it stays in your set, then you're closed. If you're talking about addition and you add them together, they stay in the set, then we're closed. Associativity, we can move around those parentheses. Identity, there exists an element that when it acts on another element, it doesn't do anything. So think of the integers under addition. If I add 0, it doesn't do anything. So that would be the identity in that space. And then there's an inverse element, such that when you do the operation, you get back to the identity. So If you've had linear algebra, you've all seen groups. Vector spaces are abelian groups. So they just work nicely with each other. So I want to study groups of links. And so this is going to be the string link group. So this gets kind of awesome. So every single link we can kind of draw like this. And then I'm just going to cut off this like outer bit here. And then my operation in the group is just stacking. So if I wanted to add two of these objects together, I would just put A on top of B. And then to make that a formal link, we just connect the top piece with the bottom pieces in order. So this is actually going to be a group. It's kind of complicated group. We actually get equivalence classes here. But this is the idea. So I have these are called string links again, and then I can go from links to string links. Here, it's not a one-to-one operation, right? There are many string links that can represent the same link. But we can look at this. What's really nice here is my choice of meridian is well defined. We just do the circle at the top for all these strands, which is really great. All right. So here's what's going on. This is the formal notation of what's happening, but let's break it down into pieces. So this is my group of links. And then I'm going to have this filtration, which is a nested set of normal subgroups. So these are going to be just smaller portions of my set contained within each other. So think very like nested Venn diagram-y thing. Um, so this top number here means the number of components I have. So I have M components. And then I'm just going to section it into pieces, calling them n solvable pieces. So this little n down here is for n solvable. And what this means is the higher the n is, the closer to being trivial I am. So, if I'm 13 solvable, I'm closer to being the identity than if I was 2 solvable. Okay. This goes into,
There's a
oh,
question.
sorry, thank you.
How do you choose meridian directions earlier on?
Oh, so the direction, yeah, good question. So I'm going to pick an orientation on my link. So we're just going to pick arrows on my normal links, set in stone, perfect. And then I'm going to pick meridians that are just going to be a loop around my component that has a linking number of 1. So when I do this one, so I will have some kind of orientation here. I was just like classic myself and lazy and didn't put in the arrows. But here, what I'm going to do is I'm going to actually pick a base point and I'm going to just wrap it around the top so I have a linking number of 1 when I look at it with this component. Yep, good question. So what I do is I kind of my first theorem of this work is saying, hey, if my link lives inside here, so I live in this special section, then all my linking numbers are going to vanish for a certain length. And by length, I mean if I'm looking at 1, 2, 3, that's length 3. So if I'm looking at mu of 1, 2, 3, 4, 5, that would be length 5. So if I live inside 0 solvable, that means all my triple linking and above have to vanish. If I live inside a 1 solvable, all my triple linking number, quadruple linking number, septuple, is that 7? Septuple, are all going to vanish. So that's some of my work is like investigating what happens to these triple linking numbers. And what I was able to do when we talk about filtrations, how we're making groups, sometimes I just want to see like what's still going on in certain parts of that Venn diagram thing. So if I want to look at like n.5 solvable links, but they're not n1 solvable, so they just kind of stop there. I showed that they have an infinite cyclic subgroup inside of them. So what I did is I took my Bromian rings, my favorite ones from before, and I did something called the Bing double. And so I just double every component and put a little claspy. So this is the Bing double of the Bromian rings. And then I can do that again and again and again and again, right? So these are really hard to draw, so no one really draws them. So here's one more step. So every component would get doubled and then add a little claspy. And I can show that this link, once I make it a string link, it has infinite order. So no matter how many times I stack it on top of itself, it will never become the identity in that group, which is kind of this little chart here where they live and things like that. Okay. So this is fun if you're very into algebra and doing classical definitions of invariants and not very diagrammatical. This is kind of where you want to sit. Oh, another question. Does this apply to all knots? Okay, so I'm going to ask a thank you. I'm going to ask a follow-up question. By this, do you mean the infinite cyclic subgroups, or do you mean the Bing double? The Bing double is an operation you can do on any knot. Totally awesome. Um, this result here is strictly for links. We don't consider linking invariants for one component. You mean the infinite cyclic subgroups? Good, 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 good. It applies um, for any component. No, the answer to your question is no. So this result is going to apply for a certain number of components. So when I Bing double, my components double. So these are only valid results for a certain number of components, and it's always going to be bigger than one. Yeah, that's a really good question. Um, yeah, fantastic. And so good. So I didn't put this on the slide, but one really good research question would be, can you get this result? This result is very dependent on doubling because doubling does a certain thing to Milner's invariance. Can you do an operation to lower that high increase of components every time you Bing double? That's a really excellent research question that I haven't had the answer to yet. So if any of you have ideas, that would be amazing. Why is it needed to prove that it will never become the unknot? It has more components, so how that would ever. So right. So for order, right, to be trivial, we would be talking about the trivial link here, which are just kind of isolated pieces. So yeah, I see where the confusion is. So when we go back here, right, so um we are looking at certain components, but now what I'm doing is I'm looking at this subgroup, but we're changing the group that we're looking at every time when I'm doubling those components, right? So we're never going to get it down to be a knot at all anymore. We are actively changing that problem. Yeah, good. So we won't have infinite. We have infinite cyclic subgroups inside of the knot group, but that's using a totally different thing and nothing with the linking number. Yeah, really good question. But when I'm talking about these stackings, um, here I would stack it and close it. I want this to be the trivial link. And we would never get a knot when we close this by construction. So we would just get, if it was the trivial link in this case, we would be able to separate those three circles away. Yeah, good. Very sophisticated questions. Very nice. Very nice. Okay. Okay. I want to shift my focus here a little bit. Um, I guess before I do that, you're asking such good questions. Do you have any other questions? Um, Before we kind of switch to more kind of a visual knot theory game.
I just wanted to ask for the Gauss linking number, does the parametrization of the knot matter in the sense that like you can have different knots like with different parametrizations that have the same linking number, right? So how exactly
Hmm.
does that work?
So, yeah, good question. So, it should be independent of parameterization. How, however, we have to be very careful there with our parameterization. The one thing that can go wrong is if we parameterize it and we have some slight overlap of the link. So you have to make sure you only transverse the components exactly once, but it is independent of parameterization. It's a good
Okay,
question.
thank you.
Yeah, very good question. Other things. There's actually there is with since you had a question about integrals, there is another integral involved in knot theory and biology with something called the average rise that we can look at a day in a strand, and that's also an interesting question. There's a formula for that. Um, I don't think I put it in. Um, but that has a problem because singularities do come up in its denominator. So that one we do have to be careful with parameterization, but that's different than linking number. But it is a question that you should ask. So yeah, great. Anything else there? Okay, I guess we'll move on to this topic. So um this is kind of a fun project my students asked me about when I was teaching knot theory this past semester, and this is going to become, we're writing a grant now for undergraduate research on it. And this is dealing with mosaic numbers. So for me, this is inspired by Saru, this game where we put down tiles and then your little like pebble has to kind of go and you're following it around and you don't want to fly off the board. So you place these mosaic tiles to create these different paths. Well, we can also do that in knot theory. A knot has a n-link has a mosaic number, and this is an invariant of a knot. It's the smallest integer for what a specific knot for which that knot can be represented on an n by n grid. And just kind of as Marcus kind of wrote in the chat earlier, this is going to be one of those minimal things. Um, so it's the smallest square grid size we can put the knot on, and it's created by these 11 tiles. Okay, so that's the mosaic number. So this is an area of knot theory that people work in. And so here are some pictures. So we have the trefoil knot on a 4x4 grid. We have the Hoff link in the middle on a 4x4, and then we have this figure 8 knot. Um, on a 5x5 grid. And we're always trying to think what is the minimal grid. We can also ask questions about the tile number, how many tiles are used here, not used in the grid, things like this. So if you are looking for just a lovely time suck, there is a knot maker mosaic here where you can start placing tiles as you wish and seeing if you can come up with any kind of knot. Here, this one's going to fail, but you can try to identify it, and then they'll be like sad, not suitably connected, and you're like, of course it's not. Or we can type in any knot here and display it. So using my tiles, this is how I can create the 910 knot. It tells me my mosaic size. Here is 7. This knot has 9 crossing. The number of tiles I used is 27. We could also start like, oh, can I like change this in other weird ways? So this is like a fun little thing if you want to play around. My students like jokingly last semester when I showed them this created a new tile bathroom like motif for me with this. Uh, oh, sorry, I had yes. So first question, why is it n by n and not n by m? Great question. We are going to deal with square stuff first, and then we'll look at rectangular stuff. So right now, the minimum we just want to keep with square. This is going to talk about some nice symmetry things a little later on. But a follow-up research question would be, okay, what is quotes the minimum like square that or rectangle we could get, or what other kind of dimensions can we get here? This is kind of where tile number comes in. Like, what are some of the unused things? Can we minimize that number as well? There are a set of Reidemeister moves with this as well. So good. Um, so right, we can set priorities here. So yeah, we can create Reidemeister moves. Can we do a kind of recursion formula to do it? Um, if we have a lot of symmetry, we can follow certain patterns for sure. Um, there are some computer algorithms that kind of go with that. Off the top of my head, I probably couldn't whip that out. But that's a good question. Okay. So great. So you kind of alluded to rectangles, which I like to see. So that is kind of a lot of papers that have mosaic numbers. A lot of their future questions are like, okay, let's take this off a square grid and see what happens. The other question is, we can tile the plane in many different ways, right? So we can tile the plane with hexagons. So there is a hexagonal uh, mosaic number and things. There's not such a nice program like the one Aaron Heap uses, but here are our hexagonal tiles. The empty one's not there, so we can start kind of changing around. We can ask questions not only about grid size, but we can start talking about how does this relate to other invariants. So does our mosaic number relate to like a naughty number or bridge number or these other invariants? So you can start asking these questions. What my students want to know is like, hey, Carolyn, I'm really into FIFA and soccer for some reason. So can I put these tiles on a soccer ball, but use different tiles, so hexagonal and then pentagonal tiles, and create things. So this is just a image I got off of my TikTok of a guy who makes custom soccer balls, and it's really interesting. So these aren't super legit tiles like for the pentagonal for a knot. But my students want to ask, like, what kind of knots can we get to show up on this kind of ball? Can we get all of them within this restriction? What are the restrictions? Can we do octagonal tiles mixed with squares? So however we can tile the plane, can we start doing these mosaic knots in there? And then what invariants can we see? So my students are coming up right now, actually, this week with a list of questions they want to ask. And then we're going to do an undergraduate research project kind of relating these things together as well, which I think is really, really great. Some people do, okay, I'm going to put different colors in here and try to only get links. And what are my restrictions there? What are the restrictions if I don't put colorings in? So there's a lot of cool questions you can ask with this, especially because we know how we can tile the planes and how tessellation things work and stuff like that. So that's what we're going to currently, or I guess futurely, look into as well. So this is kind of a fun one to think about. And then instead of soccer balls, you could be like, okay, so how can you create a torus with these tiles as well? Like, and we already kind of saw our, with our Desmos, these toroidal links. So like, how can we do that here with these mosaics would be another question to think about as well. All right, I only have 6 minutes left. So we were going to go into chemistry, so I'll just do a super fast speed run of just a mini application here with chemistry, and then I will let you have your day. Ellie's back in the background. So I am particularly interested. So I have my theoretical life, which I love to do both algebraically and diagrammatically. But I also have a really big part of my stuff is in applications of knot theory, particularly in chemical or molecular synthesis and protein folding. So I love this image right here. This is a timeline by Juan and the research group of what knots and links have been synthesized. And the first synthesis was in 1961 with the Hoff link. Throughout the years, what has been seen and what they were able to do, which I find this so fantastic. And one really good example is the trefoil knot. The first time it was synthesized as a molecule was in 1989. They used copper to help kind of take these ligands to essentially they took copper particles to help bend the molecule, and then they glued it together to create this trefoil knot. So knots and Cantonese, which are links, show up in this molecular synthesis. And the question becomes, can we use any kind of knot theory to tell if these chemicals are chiral or achiral? So are they the same as their mirror image? So here I have the limonene molecule. I have one image. It's left and right hand. So these molecules, these are mirror images of each other. And is there a difference? And in this case, there is a chemical difference. One smells like orange, one smells like lemon, depending on the chirality, the handedness of your molecule. So these are kind of fun. Right, here's another one. The right hand one smells like uh, caraway or spearmint. The one on the left smells like caraway or vice versa. So chirality kind of tells how the molecule acts. So we have this in knot theory as well. We can do the mirror image of a knot, and then we want to know if it's the same or different. So mirror image, we just kind of switch the crossings. So you can actually show that these are the same just using Reidemeister move, so retangling it. This knot is called the left-handed trefoil. It is different than its mirror image, which is the right-handed trefoil. And usually in knots, it's really hard to tell chirality if it's the same or not. There are some invariants that are good at it, but they're not 100% at it. So then we are trying to bring those techniques back into chemistry, right? For chirality. And it works. A lot of these cases work to tell the difference because some medications it matters. So here's ibuprofen. One side is just pain relief. The other side, like the mirror image, has no effect. So pharmaceuticals companies say, great, we're going to throw it in a bottle, we're done. Naproxen, one is pain relief. The mirror image is actually toxic to the liver, so they do have to separate them. And there are other forms and examples where it's kind of important to tell the chirality. So we are going to use knot theory to help us do this because we can prove so if something is achiral, right, it's the same as its mirror image. So we get this Venn diagram. So chemically achiral would imply topologically achiral. But if we do our contrapositives, if we can show topologically something is chiral, that means it's chemically chiral. So it's been a lot of work recently to take these topological techniques to show chemical chirality. So I just wanted to throw this in at the end for the people thirsting for a little application. That's not all of us, but we do see a lot of linking numbers come into play here a little bit too with links and other things to show we have the difference between mirror images, and that can show a chemical is different in mirror images as well. Someone's off mute. Hello? Okay, I think that's my time though, so I think I'll end it here. If you guys have any more questions for me, I would love to chat.
Yeah, thanks for a great talk. Yeah, so there are a few more questions in the chat now.
Oh, great. Perfect. Let me put the. What about 3D tiles, friends? Yes. I want to play with 3D tiles because my student was doing something in Minecraft and we were like trying to create something with these blocks with these tiles. So that's such a good question. As far as I know, there's not much here. There is something called lattice knots that build it at the angles and move around, but as far as tiling with a cube, I haven't seen much of that. So I think that's a really good question. If you wanted to play around, just think about the number of different combinations, though, you would have with that. You could do tetrahedron too, would be a very cool question. And how do knots behave in different geometries, flat versus spherical versus hyperbolic? Yes, friends. Okay, what a great question. It depends what we're looking at it to do. So, right, we can deform knots into different shapes. So, like, if we think about like triangles in Euclidean geometry, very straight and it's beautiful. But if it was like on spherical with a balloon, right, the angles and stuff change. The outline, though, in knot theory wouldn't change because we could deform it kind of back. So that doesn't change so much if we were looking at like different ways to parameterize in those spaces. What we would ask instead, as a knot theorist, we would be talking more about, and I think Jack just kind of nailed it here. We would be looking, instead of it sitting in like a three sphere, we would look at it sitting inside of a different manifold, like a solid torus, going inside there. It's in different homological spheres. So manifolds that have the same homology as a sphere is a very big area. And that's where people ask the questions, how do they act differently in there? And that's a whole nother minefield. That's a really good question. And Jack, yeah, like you mentioned that um that's what people are actively looking at now is how they act in different manifolds. Great. Oh, any relation to string theory, friends? Ugh, I am not a physicist. I mean, tangentially, we could probably say something here, but that would be me kind of just like pulling it out of nowhere. It, you can, there you'd be talking more about dimensional kind of aspects. So yes, there is this idea that we could talk about things being embedded in different size spaces and look at the dimension of those objects and how they interact. That would definitely be more on the physics realm. Um, are there sets of knots whose existence are open problems? If so, is there a set of turbulences and simulations that could be consistently applied to the existing? Oh, interesting question. So, are there sets of knots whose existence are open problems? So, like, I mean, if we can draw the knot, it exists theoretically. There it is. However, like, are they naturally occurring and things like that? That is such a good question. Um, and a loaded question. So in terms of my work, we ask that question in terms of protein folding. So like here are the set of knots that and links that have shown up in protein folding. Can we create a model that realizes all of those knots? And then can we be expected to eventually see the other knots that show up in the model? Um, and that has been a question by many, many people. We can create models where those knots show up, but then we get too many there. Um, in terms of like things showing up in molecules and other things, usually the idea is the simplest the better in terms of naturally occurring or synthesis. It is difficult to create something more complicated. In theory, we can do it, but nature tries to keep things as simple as possible, usually. But theoretically, if we can draw the knot, it exists to us. Um, so that's kind of nice. Yeah. You can define different families and things like that. but uh, yeah, I don't. What would the prominent open questions be? Just in knot theory in general? Oh, we have a huge, huge open question in knot theory, which is the slice ribbon conjecture, which many people have been plugging hilariously into AI to get some real interesting garbage. Uh, there are many open questions in knot theory, but the most prevalent is if the ribbon slice conjecture, which is knot is slice if and only if it's ribbon, which means slice bounds a smooth disc in the foreball, and ribbon, you can kind of close it up to have certain types of intersections. That's kind of the biggest one. There are many other open questions for sure, but that's kind of the big one.
Are there any other questions?
Your questions are fantastic, like excellent, like fantastic, kind of better than most questions I get for a talk. So thank you so much for that. Do you look at and study real life knot strains in your research and teaching? So, yeah, ish. So part of my knot theory class, we do 3D print knots, and we look at knots that way. For mosaic tilings, my student actually 3D printed all of us a set of mosaic tiles that we currently do. I do have some strains and stuff I see. I mostly use computer programming to play around with things. In terms of my theoretical work, I don't use that many tangible things. Um, but I do play around with some things, but mostly computer programming. There's a couple good programs. One's called Nottingham, which is great. Notfolio I use a lot to draw and play around. Or Notplot is also a good one we see as well. I do take a lot of pictures of knots I see in the wild though, and display them a lot, just mostly for art and fun. One thing I want to do with that question really quickly, I just bought my students a set of inner tubes. Like they're personalized, like they're small little like coolers for your drink in the pool, but they're clear, and I just got some markers so we can kind of draw around it. So I play with those tangibles. And if my students end up doing the soccer ball project with the mosaic tiles, we're going to buy some clear inflatables to help us draw on it and try to map it into a computer later. But yeah, just to help us see what's going on. So the person who had the idea of doing like the 3D blocks with mosaic cubes and stuff, we would probably try to build some things to help us see that. I think there's benefit to that.
Any other questions? Okay, so if not, then thanks again, and that concludes this part of the class.
All right. Thanks, everyone.